Here we're asked to verify the following identity. I'm going to show you two ways to approach this problem. If we start with the left-hand side first, and write the left-hand side in terms of sines and cosines, we have cosecant theta, which is 1 over sine of theta, cotangent theta, which is cosine theta over sine of theta. And because we have a common denominator, we can reduce this as being 1 minus cosine theta over sine theta. So immediately we can reduce the two terms into one nice term. The problem is that this doesn't look anything like what's on the right-hand side. To help us out a little bit, one thing we can do maybe to simplify this is to notice that we have a 1 minus cosine theta, which is one of the factors of a perfect square that might allow us to reduce the sine theta in the denominator. So if we take this and multiply by 1 plus cosine theta in the numerator and in the denominator, the top becomes a perfect square, so 1 minus cosine squared theta. The bottom is sine theta times 1 plus cosine theta. But by our Pythagorean identity, 1 minus cosine squared theta is the same thing as sine squared of theta. And we have a sine theta below. And we have 1 plus cosine theta. So one of these signs will cancel, leaving us sine theta over 1 plus cosine theta. That still doesn't look like what we have above. It's closer because now our addition term is in the denominator, like the right-hand side here. And notice that it's not too far off, because secant theta is 1 over cosine, tangent is sine over cosine. So if we think about trying to convert the numerator in terms of a tangent, if we divide the numerator by cosine theta, and divide the denominator also by cosine theta, so that doesn't change the equation at all, the numerator reduces to tangent theta. Distributing the cosine inside, we get 1 over cosine, which is secant theta, and then 1 over cosine times cosine, so plus 1. So that's one way to approach this problem. That one I think you have to be a little creative, especially in this step here, to figure out that dividing the top and bottom by cosine gets us the desired right-hand side. A possibly more direct method of proving this identity is if we start with the right-hand side and try to show it's equal to the left-hand side. So let's talk about how that would go. If we instead start with the right-hand side, and keep in mind our strategy above, take and multiply the top and the bottom of this equation by something that will allow us to evoke one of the identities that we've learned. So here, if we multiply 1 minus secant theta to the denominator and to the numerator, the denominator will reduce. This is 1 plus secant theta times 1 minus secant theta, so 1 minus secant squared of theta. And on the top we have a tangent theta times 1 minus secant of theta. Now this 1 minus secant squared theta looks very familiar. In fact, if we recall, we know that 1 plus tangent squared theta equals secant squared theta. So let's see, if we subtract the secant theta to the other side, so we get 1 minus secant squared theta, and subtract the tangent to bring it over to the right-hand side, we get negative tangent squared. So 1 minus secant squared theta is the same thing as negative tangent squared of theta. So we can replace the denominator with negative tangent squared theta. So now one of these tangents will cancel. This negative sign here can be thought of as being a negative 1 times 1 minus secant theta. And now if we distribute that negative sign inside of the numerator, we get secant theta minus 1 over tangent theta. And the final step is to divide both these by tangent. We get secant theta divided by tangent theta minus 1 over tangent theta. We know 1 over tangent theta is going to be our cotangent term. And then notice the secant theta over tangent theta, that's 1 over cosine divided by 1 over tangent or cotangent. So cosine over sine. And again, this is going to be cosine theta over sine theta. And here we get these cosines cancel. 1 over sine theta is cosecant theta. Cosine over sine is cotangent theta. So there's 2 ways to prove this problem. Both ways, I think, are roughly the same number of steps.